Hello and welcome to our day 12 lecture. Today, this is our last day with the Upward Bound Summer Academy. Just a couple things that I wanted to talk about. First of all, good job making it here. Good job making it to the end. If you've been with me the whole time, then I think you're doing well. You're going to be more than happy, number one, with your grade, and then also with with making it, making your life a little bit easier next year or the following years. Some of this stuff, it might take you a couple years to actually see in your math classes, just because of kind of what we've had to go over and how we dealt with the different areas that people are in class. So, that being said, let's go ahead and dive right into day 12. It's another day where we're just kind of looking at examples. And again, we're going to use some matrix equations. We're going to use some of those basics of matrices, but we're going to use it in a really good method, and that is to solve systems of equations. Sometimes, and I'll go right out and say this, sometimes that's not the best method, I guess, to use. I wouldn't always say that using matrices is the best way to solve a system of equations, especially one like this. I think if, I guess we're going to do it right off the bat, but, you might find after we do the matrix version, like, hey, wait a minute, that wasn't a whole lot easier. And you're mostly right. The advantage to learning the matrix method is when you have access to either some sort of software that can deal with matrices, that just makes life a lot easier. And not only can that, if that software can not only store your matrix, but they can also find its inverse and multiply and do everything that you want it to do, which, I can't stress this enough. Just an old TI-83 has it somewhere. It's hidden in some of the menus, but this is a very old calculator. So old now that it's dead, so that's good. I just haven't put batteries in it. But it will take care of it would have the ability to do any of the problems that we're going to do today. Today, just for your visual reference, we're going to use Wolfram Alpha, because, again, that's just a website that, as long as you've got some sort of smart device, some sort of internet-capable device, you can get there. But for starters, we just want to solve this system of equations like we're in Algebra 1 or beginning Algebra 2. I'm going to take this equation, I'm going to multiply the bottom by 5. So I'm just kind of giving you the layout on how I do it. Multiplying by 5, that's going to be a negative 15x minus 10y equals, gosh, I made myself think, didn't I? 70. Negative 70. Okay, and so that's going to be negative 13x. My y's cancel, and that's going to be 52. Again, negative 52. So some quick division tells me that that's 4. I always remember that one because there's 52 cards in a deck of cards, and there's 13 in each suit, 4 suits. So that's kind of, you get to learn some of those things as you progress. Let's see. Then we got to find y, and I don't have a great equation. Maybe I'll use my top one. We have 2 times 4 plus 10 equals 18. That's 8. I guess that's 10y equals 18. Subtract 8 from both sides. 10y equals 10, so y equals 1. So we get, whether you want to answer it in the form of the point where those two lines cross or whatever you want to do there. But what I want to do is I want to look at this one using matrices. And it's doable. Here's where the idea of solving these using matrices really comes from. Really, it comes from the work that we did last time. Because when I do this, 2, 10, -3, -2, when I take that matrix, which is a 2 by 2, and I multiply it by x and y, if I were to do this multiplication, how we learned matrix multiplication, 2 times x plus 10 times y, and then, so if I'm answering this multiplication problem, I'm getting this, -3 times x plus -2 times y. That looks scarily similar. In fact, it almost looks the same if I'm not going to drop the brackets yet, but if I turn that into just a minus, the plus and negative into a minus, that's what we get. Okay? And then if I say that this was equal to sort of my answers, then I could do that again down here. And the big deal here is it's kind of an unwritten rule, something that we didn't really talk about, but in order for two matrices to be the same, number one, they have to have the same dimensions. This matrix here is a 2 by 1. Well, this one's a 2 by 1. It's just got a bunch of stuff in each entry. So they're the same size, and then they have to have the same numbers and the same locations. Well, apparently, 2x plus 10y equals 18. That's what that means. So you'd say 2x plus 10y equals 18. And then you'd also say that negative 3x minus 2y equals negative 14. Those are the requirements for these two matrices to be equal and for this statement to be true up here. So just since it kind of works, this is kind of working backwards. Since it works backwards, it works in the forwards direction too. It's a really neat thing. So we're going to look at this equation right here and try to solve it. The way we wrote this last time would have been like this. 2, 10, negative 3, negative 2, times like capital X equals 18, negative 14. And so what does that lead you to believe? What do we have to do here? From thinking about solving matrix equations like we did last time, what do we have to do? Well, we have to find this inverse. Okay. We could do it by hand. Again, I'm going to use Wolfram Alpha really quick. Let me do this. Let's make this half a page. And where are we at? Come on. Oh, I'm trying to follow my mouse and it's on the wrong screen. And this is another half a page. This is a 3 by 3. I just want a 2 by 2. So I want to find the inverse of that matrix, 2, 10, negative 3, negative 2. And again, this isn't a new idea. This is what we did to find our inverses last time. And so we get some ugly numbers, but that's okay. We know that when we multiply it on the left over here, these two are going to cancel out. Technically, they give us the identity matrix. And then we're going to multiply them over here. So I want this ugly looking matrix first. I guess that's negative 1/13, negative 5/13, 3/26, and 1/13. And then we're going to multiply that by 18, negative 14. So to do that multiplication, we're going a really ugly number. That's okay. That's going to be negative 18 thirteenths plus negative 5 thirteenths times 14. That's going to be a positive 70 over 13. Okay. And let's see, let's reduce that a little bit. We'll make that a 13 on the bottom, and we'll make that a 9. I'm just kind of thinking about multiplying those in my head. 9 times 3 is 27 over 13 plus negative 14 over 13. And we can do some simplification. Negative 18 plus 70, we kind of saw that before. That's 52 over 13. And 52 over 13 is 4. 27 minus 14 is 13, and 13 over 13 is 1. So we get our same answer of 4, 1. Same answer is there. It's really cool. So you might be asking, wait a minute, like I said before, wait a minute, this doesn't seem any better. Like, I spent so much time learning how to do these type of problems up here where, you know, multiply one equation, multiply both equations. I'm good at it all. And most people are, and that's great. And that's one way to do it. It's probably the easier way to do it. That's why we cover that for 2 by 2. But then when you get into solving 3 by 3 matrices, it always feels like something has to go right when you're doing it by hand. You know, using elimination or substitution doesn't really even work. I mean, it can a little bit to find one of them, but for the most part, you're always feeling like something has to go right. And if you've ever solved a 3 by 3 system, you know, step by step like that, it probably took you the better part of a page, unless you have really small handwriting. This is a way that can make that a little bit easier. Okay, and we're going to pretty much set it up the same exact way as that problem that we just did. So I'm going to look at this. The idea on the first matrix is that I'm looking for, whenever I set these up, and I'll write it here, I'm always looking for coefficients. Spelled that wrong. Coefficients, and then variables, so coefficients times variables is always going to equal, I'm going to say my solutions. They're not really, I don't know, there's not a great, okay, there is a great word for that, and I guess I forgot it before. I would say constants. Okay, so in the first matrix, I'm looking for my coefficients, so the numbers in front of the variables. They do need to be in order. If I'm going to stick with x, y, z, then every row has to be x, y, z. So the coefficient in front of x is 1, in front of y is negative 4, and in front of z is negative 1. For the second equation, it's 4, negative 1, 4. And then we have negative 4, negative 2, negative 6. If you want to write this as like matrix X, you can. I'm going to stick with X, Y, Z so that I remember the order that I'm solving for. And then that's going to be equal to 10, negative 6, 16. Okay? Now again, we're going to do the same process. I need to know I need to know my inverse of this matrix. So I'm going to use Wolfram Alpha because, again, it's going to make life a lot easier. 1, negative 4, negative 1, 4, negative 1, 4, comma, I need one more of those, negative 4, negative 2, negative 6. Find my inverse. There it is. It's an ugly 3 by 3 matrix, but it's just a 3 by 3 matrix. So here we have x, y, z. I know that I'm going to multiply it on the left, just like before. Now let's try to write this one. So I have negative 7/3, 11/3, and 17/6. Negative 4/3. I'm going to end up making this bigger. I always write, it feels like I'm writing smaller right now, but I know once I make it full screen, it's going to look really big and a lot uglier. And then 2, negative 3, negative 5/2. Okay, so I'm going to multiply that matrix by my constant matrix. See what I mean? It always looks bigger and a little bit slanted, but that's okay. Let's go ahead and look. To do the multiplication, it's going to be a little more involved. Negative 7/3 times 10 is negative 70/3. And I never try to reduce anything at this point. I mean, I guess I will here to try to make things a little bit easier to sort of add together. Plus 11/3 times negative 6. So that's negative 66/3. Plus 17/6, or plus 17/6 times 15. I need a calculator. 17 times 16 is 252. I am going to divide that by 2 to make this another third. So this will be 136/3. Next one, we're going to go negative 4/3 times 10. 5/3 times negative 6. And again, I could reduce that, but I don't want to yet because I know I want to add all these. And then 4 times 16 is 64. Yeah. Okay. And then we have 2 times 10, 20. Plus negative 3 times negative 6 is 18. Plus negative 5/2 times 16. I am going to kind of reduce that. I'm going to think of that as an 8, and that is a 1. So 8 times negative 5 is negative 40. If you can't track that part that I was doing, just write it. Write it out. See what happens when you multiply those. You're going to get, I don't know, what is that? 80, negative 80 over 2, which is negative 40. So just trying to make things go a little bit quicker. This up here is negative 136 plus 136, so that's 0. This is negative 70 plus 64, which is negative 6/3, which is negative 2. And then this one is 38 plus negative 40, which is another negative 2. So the answer to this system of equations would be x equals 0, y equals negative 2, and z equals negative 2. And it's that easy. Whereas solving this system of equations using more traditional methods, more substitution elimination type methods, it would take a long time. And this actually doesn't take much room when you're writing it by hand. Writing it on the screen obviously makes it bigger. And then it makes it to where you can actually use some graphing software, some calculator software to make your life a little bit easier. Let's see, how many? I only have 2 more. Okay, we ought to be able to finish this pretty quick. All right, let's set our stuff up here. I have 1. It's an ugly looking 1. Negative 6. Negative 1. 4, 3, 3. And negative 6, 6, 5. That one times x, y, z. Just checking that they are all in order. X, y, z, x, y, z, x, y, z. Is going to be equal to my constants, 1, negative 24, and negative 2. So I kind of need to do the same thing. We're going to find our inverse of a matrix. 1, negative 6, negative 1, 4, 3, 3, and negative 6, 6, 5. Oh boy. That one got ugly, didn't it? That's okay though. I know that my x, y, z will be equal to yep, tough one. This is going to probably take more room than I plan on. Negative 1 over 61, 8 over 61, negative 5 over 61, negative 38 over 183, negative 1 over 183, negative 7 over 183, and then back to 61s, we have 14, 10, and 9. Yep. Shows off my great handwriting when I'm writing that big. And then we're going to multiply that by our 1, negative 24, negative 2. All right, this will get fun. Not too bad for most of it. Negative 1 times 1, negative 1 over 61, plus 8 times negative 24 over 61. So 8 times 24 is 192. And that's a negative. And then negative 5 times negative 2 is going to be 10. The beauty with all these, and I know this looks difficult, but the beauty here is still that all my denominators are the same. Next one, we've got negative 38 times 1 over 183 plus negative 1 times negative 24 over 183 plus negative 7 times negative 2, which is 14 over 183. Looks like something really cool is going to happen there. Last but not least, we have 14 over 61 plus negative 240 over 61 plus negative 18 over 61. I guess we're paying for that something cool to happen with the top and bottom rows. I don't know why I'm continuing it to be this big, but whatever. So we have negative 193, negative 183. I'm just going to write that here, negative 183 over 61. That's going to be a negative 3. Negative 38 plus 24. I actually looked at it this way. 24 plus 14 is 38. Plus negative 38 is 0 over 183. And then this one we're going to get, maybe we think about it like negative 258 plus 14. Just to check, 258, I get negative 244, and that's going to be a negative 4. So we see that we have to deal with at some point some really ugly answers, but they usually condense down a ways. So x equals negative 3. Y equals 0, and z equals negative 4. Okay, last one. 6, 5, negative 3, 5, negative 4, 3. 2, negative 4, negative 2. So that times my x, y, z is going to equal 4, 20, negative 16. Let's see. I need Wolfram alpha. And we have 6, 5, negative 3, 5, negative 4, 3, 2, negative 4, negative 2. Oh, yep, that one's getting ugly. Okay, so we see that. I'm going to write it over here. Or I'm dragging that over so that I can write this full screen. Try to make this less ugly. So my x, y, z equals this 3 by 3 matrix, 5/59, 11 over 118. And 3 over 236. I wish I could say that the last one's the easiest, but it looks like it's not saying that this makes it a whole lot harder, but it doesn't make it nice, that's for sure. 4 over 59, negative 3 over 118, negative 33 over 236. The cool thing about this one, I guess, or the different thing, I don't think it's really that cool, makes life a little harder, that in a lot of the other ones, my denominators in the rows stayed the same, and that made life kind of easy to add and subtract them. This one, all the columns have the same denominators. And that's going to make it a little bit different. Okay. And then it doesn't help that we got some bigger numbers in this constant matrix. I didn't want to undo all that. Okay. Let's see what we can do here. Let's see if I can't find a way to make this easier. I think that's 4 times that. Do I do that? I think I do. We're going to do that to try to make life a little bit better. So I'm actually going to do... No, I'm not. I'm going to stick with it how it is. This will be 20 over 59 plus 20 times 11, 220, okay. 220 over 118 plus 3 over 236. Kind of wish I would have done that. I'll talk about it in a second. 16 over 59, negative 60 over 118, and I don't know why I wrote that. That's wrong. Hold on. 33 times 16. So this one is positive 528 over 236. This one right here is incorrect. Should be negative 48. Last row here, negative 5. Negative 5 times 4 is negative 20. Yeah, 17 times 20 is 340. And then 49 times 16, 784. That's a positive 784. Yeah. Alright, so nobody ever said that we always end on the easy ones. So here's what I'm going to do. 236 is 59 times 4. 236 is 118 times 2. I'm going to turn all these into 236s. I think that that's going to make life easier. But what that means is now I have to multiply this numerator by 4 and this one by 2. Like I said, not sure if that's the easiest way to go. Obviously, if you've got a calculator that does fractions, that could be okay. Multiplying this one by 4 And that's kind of the only good part about it, is that there's an easy way to deal with these, easy way to deal with these denominators. Because I'm just thinking times 4 times 2. That one will be negative 80. And that one will be 680. So now we have common denominators everywhere. That can make life a little bit easier. The other issue is that we have some big numbers. I'm going to write all these as over 236. Just kind of an intermediate step. You don't have to do this. But I really don't like showing like me working on a handheld calculator. So I'm going to do it this way. We have 80 plus 440 minus 48, 472. And I'm going to divide that by 236. So that's 2. Then I have 64 plus 528 minus 120, 472 again. And then 680 plus 784 minus 80. 1384. Something doesn't feel right there. Let me check. 17 times 20. 340 times 2. 680. That was positive. That one's negative, that one's positive. 49 times 16. Sorry about this. 680 plus 784. Okay, that's a different number. Oh, minus 80 though. Huh. Maybe someone else can spot my mistake. Negative 20 times 4 340 times 2 and 49 times 16. Okay, going with it. So 1384, and we get, say, 5.86. Not sure if I buy that one, but we're going to leave it there, and I'll let you hunt around for a mistake if there is one. I'm not saying there isn't. I do make mistakes, so if you find it, you find it. If not, let it go. I hope you had a good time. I had a good time. I'm proud of everybody that made it, and good luck in the future. Get done with the task presentation and the post-test for me, and we'll be good to go. Have a good day. See you in class.